My name is Brian Cunningham. I'm with ELPRO Technologies. Today's webinar, we're going to talk about how to set up Modbus communications on the 415, 915, and 215 series of radios. The first thing to chat about is what exactly is Modbus protocol? Well, for one, it is the world's most popular industrial protocol. I Googled it, and it looks like there's something like close to 8 million installations of Modbus networks around the world. Originally, it was created by the Modscan Corporation, which was purchased by Schneider Electric way back in 1979. And that's when they came out with the first iteration of Modbus, which was Modbus RTU. And it operated on a RS-45 daisy chain. And Modbus is valued for its simplicity. It really is absolutely a dead simple protocol, especially when compared to all of the other protocols that are out there on the market, like 802.11. Even Allen Bradley's Ethernet IP is substantially more complicated. And as well, Modbus is an open protocol, so there's nothing proprietary about it. You don't have to pay any royalties to Schneider Electric or anything to be able to use it, to have it designed or built into your product. And there's an organization, modbus.org, which promotes the use of the protocol and the modernization of the protocol as time goes on. Modbus is really simple. It just uses two-step messaging. So the master device requests the data, and the slave device replies with the data. So there's just simply two transactions that take place, and that means that there's very minimal overhead or minimal bandwidth required. Initially, here we go, is an RS-232 protocol, and later on they developed Modbus TCP, whereby they essentially took the Modbus RTU messages, wrapped it in an IP Ethernet packet, and now they can send it over Ethernet networks. Okay, let's just get this our slide to advance. There we go. Okay, so there are, as we mentioned, there's two versions of Modbus. We have Modbus TCP, which is over an Ethernet network, and Modbus RTU, which is over a serial network. So I'll start on the right-hand side here. Modbus RTU serial protocol over RS-45 or over RS-232. By far, RS-45 is far more common. And this is because RS-232 is limited to point-to-point, whereas RS-45, we can have a daisy chain network. So we can have one master device and then up to 32 slave devices. And with a shielded twisted pair of RS-45 wiring, the cable length can be up to 4,000 feet. However, there are some data rate limitations on that. Typically, you can get 4,000 feet if you use the lowest baud rates available. But if you start bumping up the baud rate up to something like 115 kilobits per second, then the cable length is going to get a little bit shorter, quite a bit shorter than that 4,000 feet. Okay. For addressing, Modbus RTU uses a device ID, and the master device and all slaves must have a unique device ID. There is only one master on every network, and there can be up to 32 slave devices. I should say slave nodes, not modes, nodes. In terms of master mode, the master device, it initiates all request messages. So a slave will never produce any data or never transmit anything unless it is responding to a request message from the master device. In order to get these messages initiated, you have to create Modbus master mappings to request the data, where you have to specify which slave device you would like to get the data from. You have to specify what registers and what register type. And we're going to jump into all that in a couple of minutes here. The Modbus request messages can be either read or write, and that just determines the direction or the flow of data. Is the data flowing into your device, or is it flowing out of your device? And I'll show you some examples of that in a few minutes here. In slave mode, it only responds to messages. So it does not transmit anything unless it has a request message coming from the master device. And slave mode is really simple, very minimal setup required there. Okay, later on in time, Modbus TCP came out as Ethernet became more popular. And so Modbus TCP messages can be sent over any Ethernet network. So that would mean radio networks, that could mean cellular networks. It can be passed through Ethernet switches, etc., etc. The addressing of each individual device now uses IP addresses. Whoops, oh, sorry. Accidentally bumped us ahead one slide here. Client mode is now what we call the master device. And the client initiates all request messages, and the client is the device that must have the Modbus mappings in it to request the data. And of course, similar to RTU mode, you can either write or read data from a server device. The server mode is the equivalent to the slave, and it only, like Modbus RTU, it only responds to messages, and very minimal setup is required there. Okay, let's head to our next slide here. There we go. So here we go. This is showing a typical Modbus RTU layout. The wiring is referred to as a daisy chain. And RS-45, as I mentioned earlier, is by far the most common method, although it could be RS-232. So what we do is we wire it in this fashion here, whereby we have this long daisy chain. Now we have to keep the wires going to each drop as short as possible, because there are some capacitance issues that occur if you have a T and you have some lengthy wires going off to each slave. And we can have up to 32 slave devices all connected. And over here we have our master, which initiates all messages. And the messages, the outbound messages, head to the slaves. The slaves reply back to the master. Now, one thing you may have noticed on most ELPRO radios is that we have a RS-45 termination resistor built into the radio. And the RS-45 termination resistor, it just looks like a squiggly line. It symbols the resistance. It uses the resistor electrical symbol, and it's on the bottom of most radios. So you'll see a small switch whereby you can enable or disable that termination resistor. The termination resistor should be enabled on the end points of an RS-45 daisy chain. The middle devices must not have that RS-45 termination resistor enabled, otherwise it will cause some issues. The purpose of that termination resistor is to prevent reflections from coming back on long cable lengths. So for example, if the most distant slave were, say, 200 feet away from the master device, then it's possible that when that slave tries to put a series of ones and zeros on the 45 daisy chain, there could be some ringing effect, and there could possibly be a reflection that comes back, and that can distort the signal. Therefore, by putting the termination resistors at the endpoints, it gets rid of that ringing effect and that echo that can possibly come back. Now, if the wiring is very short, if the wiring is less than 10 feet, and no termination resistors are required, if they are enabled or disabled, it will have no effect whatsoever. It has to do with the cable length and the capacitance of that cable. The greater the capacity, the more current that is required coming out of each RS-45 device to produce a digital 1 or digital 0. Okay, Modbus TCP has this format here, whereby there are far fewer restrictions on the layout of the network. And you can have, in this case, multiple master devices, or in this case, multiple client devices, all querying remote Modbus servers. The addressing is done by IP addresses, just like any other Ethernet network. And then down here, we have a Modbus TCP to RTU converter device. And this is what all of our radios are capable of, as well as some of our other products, like our 945 and 245 Ethernet pass-through modems, as well as the 645 M-4 cellular modem as well. And they can take a TCP message, convert it into Modbus RTU. So now you would have an RS-45 connection going to these older Modbus RTU devices. So we can combine Modbus TCP and Modbus RTU in the same network in this fashion. Okay, now here's what the Modbus message structure looks like. And it's really very, very simple. If you break down the message coming from a master device, the first couple of bits will be a couple of bytes rather, will be the device address, followed by the function code, which determines what you're going to do, if you're going to read inputs, write two outputs, or read single bits, as opposed to reading 16-bit registers. The next is the data requested from the specific location on board the slave device. And then lastly, there is a CRC error check included. The response from the slave, structured very, very similarly. It specifies a device address, then it specifies the function code, and it includes all of the data. And then lastly, the CRC error check. So a Modbus request message is typically very short. I forget exactly how long these are, but these are going to be maybe 10 or 15 bytes of data. So extremely small packets, very low bandwidth requirements. The responses can be much larger. I think the maximum response size is I think it's limited to something like 512 bytes of data. But we're talking about bytes of data, not kilobits or megabits or anything like that. So the throughput you require on a radio system that is transmitting Modbus is very, very low. And from the previous webinars that I've run, as you all probably know by now, the lower the bandwidth, the greater the range, or the greater the distance of that same radio system. Over here, this just describes the standardized Modbus function codes, and we can read coils or digital inputs, and we can write to coils and that sort of thing. And this also shows you the register naming structure. Now, digital coils will be addressed from 0 to 10,000. Digital inputs will be addressed from 10,000 to 20,000. Input analog inputs will be registered from 30,000 to 40,000, and analog outputs will be given registers numbers 40,000 to 50,000. So these are the function codes. They're standardized across Modbus devices. By the way, when I say standardized, they're, I would say, about 95% standardized across Modbus devices. Some manufacturers have put in additional features that might not exactly conform to the Modbus standard, but with our ELPRO products, we don't necessarily support all of these function codes. We just support the most important ones that are required to be able to read digital inputs and outputs, and analog inputs and outputs. Okay, so yeah, just a bit of history on, a bit of an explanation on the Modbus messaging format. Inside of ELPRO's 915, 415, and 215 U2 radios, this is the addressing scheme that we use. For digital inputs 1 through 8, if the Input, if the DIO is being used as an input, it starts at register 10,001. If it's being used as an output, it starts at register number 1. Okay, so we have 8 inputs on the radio, and our numbering system starts from 1. Other manufacturers' numbering systems sometimes start from 0. So if that were the case, you would see digital input number 1 being shown as input 10,000, not 10,001. So it's important to remember that there can be a 1 register offset between different Modbus devices depending on where they start their initial register. For the analog outputs on the radios, they start at register 40,001. The analog inputs at 30,001. Now, we also have a couple of diagnostic registers. The power supply voltage is register 30,005. And if you happen to have a battery connected to the input of the radio, the battery voltage will be shown at register 30,007. Okay, so those are some two fairly important registers that are often monitored along with the analog inputs, just to make sure that the radio's got proper power and everything's functioning normally. Now, for our scaling, 0 milliamps coming into an analog input will be scaled at 8,192 decimal. 20 milliamps will be scaled at 49,152. The idea behind this scaling was that 32,767, which is the midpoint of a 16-bit register ranging from 0 to 65,000, that 32,767 will be the midpoint of a 4 to 20 milliamp loop. Now, Modbus uses, for the analog points, they use 16-bit registers. Therefore, in decimal, these values can range from 0 to 65,536. By the way, you might notice my little shortcut. I just usually say it's 0 to 65,000. The exact number would be 65,536. Okay, so this is how we scale our inputs, and these are the registers you would need to read and write from to be able to access the analog and discrete inputs on the 415, 215, and 915 U2 radios. Okay, so now to get to the heart of it, how to set up Modbus RTU slave mode. And what we're going to do is I'm running through all the possible modes. So we're going to talk about RTU slave and master mode, and then Modbus TCP client and server mode. Okay. Now, with the 915 and 415 U2 radios, we have a Windows-based configuration utility. So setup is pretty straightforward. It's much simpler than using the web pages. The web pages are generally used for diagnostic purposes. So with the 915, the 415, and the 215 U2 radios, you can run a browser, type in the IP address of the radio, and up pops the configuration and all of the diagnostics. Alternately, for the 915 and 415, we have a Windows-based program for configuration. So the process for setting up Modbus, first of all, we need to run our meshing configuration utility, or if it's the 415, we run our device configuration utility. These are separate programs, but they are very, very similar, and you'll see a lot of overlap between them. The next step is we select RS-485 in the project or in the tree below the radio module. Then we go to the operating mode and we set it to Modbus RTU slave. Then we make sure that the baud rate, data format, and flow control match the external device. So the external device would have to be set to 9600 N81. And then lastly, we set the device ID. The device ID has to be different from all devices on the network. So the master, all of the slaves, they all have to have a different device ID. Okay, on the 415, virtually identical setup here. Very, very similar to the 915. And really, that's it. From this point, we would just click on the title of the radio. We would click on Program Unit, then to transfer this configuration from the software into the radio. So slave mode is really, really dead simple to set up. Oops. Okay. Now setting up slave mode on the 215U2. Because this device does not have a Windows-based program for configuration, it's really designed as a fairly simple, quick networking device. What we do is we run our browser like Firefox, and we type in the IP address of the radio. Then we type in our user and password to be able to log into it. And the next thing we have to do is we have to click on Serial. So over here, we can see Serial on the right-hand side. Then within the Serial tab, we scroll down until we see the RS-45 serial port configuration. We select Modbus RTU slave as the RS-45 port type, and the data rate and format we set to match the external device that will be wired into the RS-45 terminal block on the radio. Lastly, we set the Modbus slave device ID. And after we've done that, we just head down here and we click Save and Activate Changes. And presto, this device is set up for Modbus RTU slave on its RS-45 port. Okay, then the next thing I'd like to discuss is setting up a Modbus TCP server mode on either the 915 or the 415 radios using their Windows-based configuration utility. So just like we did with the RTU modes, first of all, we run our configuration software, either the meshing configuration software for the 915 or device configuration utility for the 415. Then we click Modbus in the tree structure below the name of the radio. And then we head over and we make sure we have a tick mark in Modbus TCP Server enabled. Whoops. Oh, my apologies. I think I've gone ahead one slide a little bit faster. There we go, previous slide. Okay. Sorry, this mouse is a touch sensitive here. So once we have set Modbus TCP Server enable, we are complete. And this is because it uses the IP address of the radio for the addressing. Now, I will state one thing here that I have not been able to find clarity on, and that is whether this device ID is still applicable in Modbus TCP. In chatting with my counterpart in Australia, we cannot see a logical reason as to why it is, but this is something personally I'm still a little bit unclear on. And so my suggestion is simply make devices IDs unique from every device. A very simple solution. We know that will work for sure. I have to emphasize, I'm not sure if it makes any difference or not, but I do know how to make sure it's not a problem. And that's just make every device ID different on every Modbus TCP device we're dealing with. Okay, once we're done here, we just go ahead and we click on the title of the radio. We click on Program Unit, and that sends the configuration from the computer into the radio. Okay, in the 215U2 radio system, what we would do is we run our browser and we log into the configuration menu for the radio. We head over here and we click on Modbus TCP. So we click on Modbus TCP and up pops this menu here. And then all we have to do is put a tick mark in Enable Modbus TCP Server. And again, the device ID, just make sure everything's unique and we'll never have a problem with it. Lastly, we hit Save and Activate Changes, and presto, this product will now act as a Modbus TCP server. Okay, then the next thing I'd like to chat about is setting up master mode, and then we'll go on to Modbus TCP Client mode, which are both essentially the same, just a different interface. To set up Modbus RTU Master on the 915 or 415 U2 radios, we just go ahead, run the configuration utility that's going to be very similar between the two devices. We click on Modbus, and then we head up here, and we click Modbus TCP Client and RTU Master. Then we have to head over to the RS-45 Modbus parameters. We set it to Modbus RTU Master, and then we make sure that the baud rate and the data format match the external device that it will be wired to. Down here, we've got some of the other details, like how often the radio will scan the Modbus slave device for data. In this case, we've set it for once per second, but we could certainly set it faster if we needed. And this is the response timeout is how long the radio will wait for the slave device to send a reply. In this case, it's going to wait 1 full second for the reply. Once we have gone ahead and set up the serial port parameters for the radio here, we need to create the mappings. The mappings are created by clicking under Add down at the bottom of this menu. Once we click Add, we'll see this new menu pop up. The first thing we have to do is we have to select the command type. There is either read or write available, and when you select one of the two, you'll see this arrow appear. A read will transfer data from the slave device into the master radio, and if we select write, you'll see the arrow switch directions, and we will be sending data from the master radio into the Modbus slave device. Okay. Once we have selected the direction of data flow, we go ahead and select the register type. So then we have to tell it, are we transferring digital inputs or outputs, or analog, which are called register outputs or analog inputs here. In this example, I've selected digital inputs. As soon as we do so, it automatically starts and shows you register 10,001 as a typical starting point, because digital inputs are from 10,000 to 20,000 in Modbus's registering structure. The next, we have to enter in the device ID of the slave unit. And I know I've got a device ID of 1. In the previous menu, you saw that I had the radio also set as device ID 1. So this would be an error. This device ID has to be different from what is in the radio. Okay. Then once we have set up where what's happening on the slave device, then we can head to the local register on the master device, which is our radio. So you can either click on this pull-down menu, and it'll show you digital outputs 1 through 8, or you can click on the ... and it'll show you all of the registers that the radio has available. And there's a couple of thousand registers. Many of them are just generic purpose that can be used for any input or output. Next, we select the I/O count, and this determines how many consecutive registers we're going to transfer. So if we set an I/O count of 5, we would be gathering registers 10,001 through 10,006, and they would be going to I/O points of 10,000, or sorry, digital output 1 through 5. Okay, so they take consecutive registers and map them from one to the other. Lastly, fail register. what this is this determines this provides an indication if this mapping is successful or unsuccessful. So if digital output 8 on the radio is not being used for any other purpose, use it as a fail register. And that is because there is an LED next to each digital output. And if this mapping is unsuccessful, maybe the wiring was not correct, we got the device IDs wrong, or something about this mapping did not work, the LED next to digital output 8 will turn on. So then once we fix the problem, get it all working successfully, and once it successfully, once the message receives a proper reply, the LED next to DO8 will turn off. So it provides you a visual indication that communications are successful. So these fail registers, you can use them for wireless mappings as well for the same purpose, but make sure to use a different fail register for each mapping so that you can tell which one worked and which one did not. Okay, so once we have set up our Modbus mapping, this one here is showing an example of transferring an analog signal. Previously, we showed transmitting or sending a digital signal. This one is showing a write command, taking analog input 1 and transferring it to register 40,001 on the slave device. So in this case, you can see the command type was set to write. The arrow now points to the flow of direction. And once we have that, once we select our analog input, first of all, we select the register outputs, and then it automatically assigns it to going to the 40,000 series registers on the external device. Then we go ahead and select which input we would like to be sending over there. And then we select the I/O count, as in how many of these analog inputs did we want to transfer to this external device. Lastly, we have our fail register. So in this case, I'm using DO7 because in the previous mapping, I used DO8. And this way I can tell if this write mapping was successful just by observing the LED next to digital output 8 on the terminal block. Once we're done, we hit apply, and then we have our list of mappings down here. So this is under the Modbus menu that we looked at a few minutes ago. And now that we have added these two mappings, you'll see this information at the bottom of the screen. When we say local register, we mean the register on board this radio right here. Okay. The I/O count is the number of registers we are transferring. The function code, in this case, we're just summarizing as read or write. You don't have to memorize, function code 12, function code 16. That's because the Windows-based program looks after that for you and makes life a fair bit simpler. The destination here is the register number on board the external device. And lastly, this is the device ID of that external device. Okay. And I guess these would be the final points here. The COM fail registers, DO8 and DO7, those LEDs will be on if these mappings fail, and they will be off if these mappings are successful. So quick visual indication of proper operation. Okay, so Modbus TCP Client mode. Very similar to Modbus RTU mode for the 915 and the 415. So we're in our configuration software. Again, we've just clicked on the Modbus setup there. We make sure that we have a tick mark in the Modbus TCP Master Client and RTU Master box up here. And then we click on the Modbus TCP Client tab here. Then we have to click Add to create the mappings that we talked about just a minute ago with some slight variations. So in the Modbus TCP mapping menu, the only real differences you're going to find are now we have an IP address and a port number that we have to enter in. Okay, so you can see we still have this device ID in this box right here. And again, as I mentioned earlier, I'm unclear on its impact when we are dealing with Modbus TCP, but I do know how to make sure it does not cause a problem, and that is to make sure that every device has a unique device ID. Okay, so once we've went to start, we type in, we enter the command type. We have read or write available. Then we indicate the register type, either digital outputs or register outputs. Then we enter in which local register, so this is on board the radio. In this case, DI1, that we wish to send to the external device. We enter the I/O count of how many consecutive registers. And then over here, we enter on the external Modbus TCP server device what register number we would like that to go to. Okay, I've decided to use digital output number 6 as the failed register. And this is the IP address of the external device. Whoops. Oh, I've made a slight mistake. It's usually 168, and not 169 there. And then Modbus's port is always port 502. It's never anything different, always port 502. Okay, then we go ahead and hit apply. And now we can see this mapping in our Modbus TCP Client mappings list. Okay, in this case, the function code, we are providing a little extra detail. It's function code 15, which is write coils. Okay, and then we have the server IP address right here. It's truncated a little bit. If I expanded this, you would see it, et cetera, et cetera. The rest of the parameters will be identical to Modbus RTU Master mode. Okay, to set up Modbus TCP Client on the 215U2, it's going to be very similar, but the layout is going to look a little different. So, of course, we log into the 215U2 via the web pages. Then we have to click on Modbus TCP over here, and this will bring up this menu that you see in front of you here. Then we have to click Modbus TCP Client Enable, so we have to make sure there's a tick mark in that box. Next, we have to click Add Entry to create the TCP client mappings. So the first box, in this case, I'm transferring analog input 1, which is register 30,001. Now this information will be in the user manual, and of course it was in the, I think about the 4th slide that I presented earlier today. But just keep in mind the configuration utility, there's a good reason why we developed it for the 915 and the 215 products, because it fills out a lot of these details for you. You can just select analog input 1, and you don't have to go to a lookup table to figure out that correlates to register 30,001. Then we have our I/O count. We're just transferring a single 16-bit register. Then we select our function code, and there are about 5 or 6 function codes that we support. They should be fairly obvious. You've got read registers, write registers, etc. And then this is the destination device. Now, this will actually be going to register 40,001 on the Modbus TCP server device. However, because the function code specifies write registers, it's automatically going to go to the 40,000 series register. So we only need to enter the value of 1, knowing that it will automatically be going to register 40,001. Okay, then we have our mysterious device ID, which we just make sure it's different on every single device. Then we have the IP address of our server device. The server port, always 502. And we have a response timeout, in this case 1 second. And this is our COM fail register here. So this would be digital 8 or digital output 8 on the radio. This LED will turn on if this message is unsuccessful and turn off when it is successful. So once we have our mappings created, we go ahead and hit save and activate, and presto, we now have this 215U2 acting as a Modbus TCP client. Okay, once we have gone ahead and set up the device, because we are integrating two pieces of equipment together, often there can be some subtle differences between manufacturers as to how they've designed their products. So again, the device ID, simple solution, just set everything to a different device ID. Another common issue is the register numbering start point. Some devices, the engineers have designed their products to start the numbering at 0. So in some cases, analog input 1 would in fact start at register 30,000, not 30,001. So if you're getting an error message, try offsetting that register number by 1 in either direction. For troubleshooting, if you're trying to read a block of registers, keep in mind that with Modbus, if there is nothing in the register, in other words, that register has not been initialized, Modbus will ignore the message and the mapping simply will not occur. It will not, if it's a slave device, it will not reply. And if it's a master device, it will not, doing a write command and there's nothing in the register it's writing from, it will ignore the message. So just keeping that in mind, there must be data in these registers. They cannot be uninitialized. And in our 415 products and the 215, etc., we have something called fail-safe blocks. And that allows you to, part of the fail-safe function is it allows you to initialize a register upon power-up. So you can say, I want a value of 1,000 in all of my analog inputs upon power up. So there is something there, but it's outside of the scale of 0 to 20 milliamps. So the Modbus mappings will be successful, and it'll be up to the external controller or whatnot to realize that, oh, that's an out of range value. I know this this mapping is successful, but there's an out of range value in it. It probably just has not been updated as of yet. Okay. So as we mentioned earlier, some devices use a function code, like we saw function code 16, write registers to determine if the 0, 10,000, 30,000, or 40,000 registers should be indicated by using a 1 instead of 30,001. So this is another thing. Sometimes it's really simple, just trial and error. Try entering 1 or 30,000. In our devices, of course, we know exactly what these numbers should be. It's the external devices that sometimes, if you're using them to write, if you're using an external device to write to the radio, in other words, the radio acting as a server or a slave, sometimes a little experimentation on the external device can figure out whether it should be 1 or 30,001, for example. On the RS-45 line, I would say probably 10% of the time, customers have accidentally reversed the polarity. Because it's really simple to figure out if the polarity is reversed just by pulling the wires out and swapping them around. You will not cause any damage to the radio or generally to any RS-485 device if you do so. Swapping the polarity can be a very quick check for those 10% of installations that we run into there. Then we also want to look at the RS-45 LED on the device. In our devices, we have a single LED for RS-45, and it flashes green when transmitting, red when receiving. So what we should see is we should see a green and red flash in tandem as the message transmits, then receives a reply, transmits and a reply, and that sort of thing. Okay. If the Ethernet does not work and you're using Modbus TCP, check the LEDs on the Ethernet port of your device. There are these amber and green LEDs on the RS-45 jack of a computer, and they should be on when they are connected to another device, or on or flashing or something of that sort, but they both should not be off. Okay, and then lastly, with Ethernet devices, try pinging everything just to make sure you can still get through. So try pinging the remote device, try pinging the radio, and once we've confirmed we know what our IP addresses are for everything, we'll be a lot closer to getting the network up and running. Okay, then we have the option, we can test using a tool like Modscan software. Modscan is produced by a company on the East Coast, and it acts as a Modbus Master. They also have a Modbus Slave or Modbus Server device, software that you can purchase from them as well. This software program is not expensive, and it is an excellent tool for figuring out which device of your Modbus network is not communicating. So what we would do is we would click on connection. We would tell it how we are going to connect. And if you hit this pull down arrow, you'll also see COM port 1, COM port 2, or Modbus RTU. In this case, I set it up for Modbus TCP. Then what we have to do is we have to enter in, I was testing the radio, so we have to enter in the IP address of the radio that your computer is connected to. Then we have to enter in the port. It's always 502, and we go ahead and hit OK. Okay, and here we go. This was what I was able to read off of a 415 U2 radio system, and I read analog inputs 1 through 4. Now you can see I had nothing wired into the inputs, so they're all at 0 milliamps. So this is why they're all showing the same value of 8,192. We can see one of them is 194, but typically the accuracy is going to be plus or minus, I think I looked it up a long time ago, it's about plus or minus 10 or 15 byte counts. So usually it'll show you exactly 8192, but if it shows 8194, well within the specifications of accuracy for the radio. You're literally splitting fractions of a hair at this point here. I entered a length of 4, so we're reading 4 consecutive data points, and the starting address is 1. And because I selected the function code of 4, which is to read input registers, it automatically adds 30,000 to this address number right here. Okay, then the device ID up here, this matches the device ID I had inside the radio. Again, I'm a little bit unclear on that. And presto, we have successfully read using Modbus one of the analog inputs on the 415 U2. Okay, that's it for today's webinar.